Okay, we'll start off with the homework problems. These were the ones I assigned. So, alright, so it's 17, number 11, in this ternary system here. This is the phase diagram. You see a liquid, this is a two-liquid miscibility gap. This indicates this is different temperatures. These would be the tie lines, as the liquid at this end of the tie line is in equilibrium with the liquid at this end of the tie line. This isn't the whole phase diagram, but this is the liquid phase. There's a dome that comes up here, and these are the tie lines of this particular temperature. Okay, so why is there a miscibility gap? The miscibility gap is entirely within the ternary system. It does not abut the binary systems. It comes around like this, and it's centered along here. How would you explain that in words? Well, it's like the systems that we talked about earlier. If you have A, B, C, here you have strong short-range ordering, like to form A, B nearest neighbors, and here you don't. Then you tend to get positive deviations along this join. The positive deviations because the A's and the B's like to stay next to each other. And if you add C, you're forcing the A's and B's to come apart, and that's giving a positive contribution to the Gibbs energy. Okay, so you always have, if you have complexing strong here, by adding C to the AB, you're breaking up the AB bonds, which are strong, so the AB bonds prefer not to be broken up, so this gives you a tendency to demixing. If the positive deviations are strong enough, you will actually get a miscibility gap along that line, the two-phase region. In this case, the calcium and the phosphate, obviously, at this particular composition, form a strong complex. The calcium and the phosphorus tend to stay close to each other at a ratio of 3 calciums to 2 phosphorus, whatever that structure might be. Presumably over here, in an iron phosphate system, you would get a similar tendency for the iron and the phosphate to stay together, but it's not as strong as it is over here. There's a stronger complexing here than there is here. So again, if you add the iron to this complex, you're breaking it up, so you form a, okay, this is quite normal. If you have strong negative deviations along one side and not the other side, you tend to have this type of thing because of the short range order. Or not even because of the short range order. Even if you don't have short range ordering, even if it was a random Bragg-Williams mixture, as you're adding C to AB, you're breaking up the strong AB bonds. Actually, I showed before that if you have Bragg-Williams mixing, you actually overestimate the positive. You actually overestimate the positive deviations because the A's and B's can't even cluster. You're just breaking them up. If you have short-range order, they can actually cluster within the single phase and lower a little bit. Anyway, but you always see these things. If you have a system like SiO2 with FeO and CaO, you're going to see exactly the same thing. Replace phosphorus by silica, and you'll have a calcium silicate, which is stronger than an iron silicate cluster. 11.6, solution of carbonates. Okay, the system sodium carbonate, lithium carbonate is a simple eutectic system. Suppose that the solubilities of the solid state is negligible. Calculate the temperature as well as the composition of the eutectic. You're given the heats and temperatures of fusion of the pure salts. The phase diagram then is a simple eutectic phase diagram. Marking. Simple eutectic phase diagram with sodium carbonate. Over here you have lithium carbonate versus temperature, no solid solubility. Calculate the temperature and composition of the liquidus. You're given the melting points of the pure carbonates, 850 and 720, and you're given the heats of fusion of sodium and lithium carbonate. And assume that the liquid is an ideal Temkin solution. An ideal Temkin solution in the liquid state is one where as I said, the cations mix randomly on their lattice and the anions mix randomly on their lattice. And the ratio of the lattice sites is given by the ratio of the number of positive and negative ions. So if we're going to solve this, then remember the activity of sodium carbonate now is the mole fraction of sodium squared times the mole fraction of sodium carbonate. Or maybe another way, if you want to look at this, is let's do it differently from this. The thing is, you have a mixture of sodium carbonate and lithium carbonate. Okay, but every sodium carbonate actually produces 2 sodium ions. So as we've written it here, you really have 2 moles of lithium sodium ions mixing with 2 moles of lithium ions. Okay, so you've got twice the mixing entropy. Okay, so one way around it is let's redefine the components as sodium carbonate 1/2, lithium carbonate 1/2. In that case, if you define these as your components, then you have a regular, then the activity in this system, the activity of sodium CO3 to the 1/2 in this ideal solution is the mole fraction of sodium carbonate to the 1/2, which is the same as the mole fraction of Na2CO3 in the other system, right? And the activity of lithium carbonate to the 1/2 is the mole fraction of lithium. Let's make this simpler. Let's just call this distance here x, going from 0 to 1. Okay, the activity of sodium, I want to write all this under. The activity x, whether you're talking about x is the mole fraction of NaCO3 of LiCO3 1/2 if you define your components this way, but it's also the mole fraction of Li2CO3 if you define your components the other way. You don't change by redefining your components, you still don't change the value of x at any composition. So the activity of sodium carbonate to the 1/2 is still 1 minus x. The activity of lithium carbonate to the 1/2 is x in an ideal solution because you're mixing 1 mole of sodium and 1 mole of lithium. Okay, but now the difference is that the heat of fusion of NaCO3 1/2 is 1/2 the heat of fusion of Na2CO3. That's where the difference comes. That's why you have to redefine it this way. So in that case, I could write for the sodium carbonate liquidus, I could write RT log activity, or log of the activity of NaCO3 1/2 equals minus the heat of fusion of NaCO3 1/2, 1 minus T over T fusion, the equation of this liquidus. I write the same thing for this liquidus and calculate the intersection point as we've done several times. The difference is this is the heat of fusion of NaCO3 1/2, which is 1/2 the heat of fusion of Na2CO3. Okay. If you don't do that, you get obviously a very wrong answer. Okay. If you were simply to consider these to be Na2CO3 and Li2CO3 as your components, and you wrote it this way, and you wrote the heat of fusion of Na2CO3, you would have twice the. This then, of course, is still 1 minus x. Suppose I wanted to define it in terms of Na2CO3 and Li2CO3. In that case, this is the heat of fusion of Na2CO3, which is twice before, so I've got to put a twice over here. Okay, so I simply have twice the entropy. In other words, if I'm taking this and this is my components, the entropy of the del S of mixing is minus 2R x log x plus 1 minus x log 1 minus x. So the 2 would go over here. Or the activity of Na2CO3 is the activity of NaCO3 to the 1/2 squared. So in other words, I could put the square up here. The activity of Na2CO3 is 1 minus x squared. Okay. But this is where it's extremely important. If you do the 2 sodiums and the 2 lithiums go in as independent particles, or do they go in as, say, a molecule? If this was a mixture of molecules, if this was Na2CO3 mixing with Li2CO3 molecules, which it isn't, then you would do it the old way. You would have to, then it would be 1 minus X, and this would be the heat of fusion of Mn2CO3. But this forms two particles of sodium, which are independent. This forms two particles of lithium independent, so you've got twice as much entropy. So you're getting twice as much Gibbs energy for every mole that you add. So it lowers the liquid is it? Okay, there are some other examples of this, and let's do then this. Okay, 203. This was in section 30 here. Final exam. Okay, question 1 is pretty much the same thing. System lanthanum chloride. Lanthanum fluoride is a simple eutectic system. The eutectic temperature is 644. This is virtually the same idea. Assume a regular term for the enthalpy of mixing, and assume that the entropy is given by an ideal Temkin model. So once again, when you're mixing them, the cation sublattice is occupied by the lanthanum, so that's the same, but here you have 3 chlorines and 3 fluorines mixing. So for every mole of LaCl3 and LaF3, you're getting 3 moles of mixing. You really have 3. This is really 3 moles of particles that mix, it's not 1 mole. That's the important thing. You're given the heats of fusion and so on. And I put this on the computer. It did tend to end up a bit not very great reproduction. But anyway, there's your phase diagram. And the RT log activity of lanthanum chloride then along this liquid, this is 3 RT log mole fraction of lanthanum chloride. You have 3 times the entropy because you got 3 moles of chlorine mixing with 3 moles of fluorine, plus your regular term omega X squared lanthanum fluoride, and that's equal to delta H of fusion 1 minus T over T fusion. And here I've used the LaCl3 heat of fusion because I put the 3 here. The other way to do it would be to make this La1/3 Cl, remove the 3 here, divide this by 3, and divide this by 3. Comes out the same thing, obviously, if you take 3 out of here. Assuming then you're redefining your moles as La1/3 Cl, La1/3 F, you're dividing every term by 3, and it comes up to the same thing. And you do the same thing for the other liquidus, for the lanthanum fluoride, 3 RT X lanthanum fluoride plus omega X squared lanthanum fluoride. Is that, and then you solve the 2 equations however you want to get the answer. You know the temperature, I think, what was it? You know the temperature, you want to calculate the composition. So, temperature of the eutectic is known. You can calculate the composition by an iterative guessing procedure. Okay, but the point, of course, is the 3 that's here. The activity of LaCl3 is 3 RT log XAL LaCl3. Or if you want to redefine it in terms of 1 mixing particle, which is another good way to do it, the activity of La1/3 Cl is RT log X. Same X, same mole fraction, doesn't matter how you define it, the mole fraction still stays the same, but every term, all the terms over here then are divided by 3. Specifically, the heat of fusion of La1/3 Cl is 1/3 the heat of fusion of LaCl3. Okay, so this is the Temkin model. For a liquid in which you're assuming that the fluorines and chlorines mix on their lattice sites, and the ratio of the lattice sites is 3 to 1 because that's the ratio of the cations to the anions. Okay, now 2003 final exam number 3 is more complicated. No, sorry, no, I haven't got to the complicated one. Just a second. A client asks you to estimate the temperature. You're going to do an optimization or something to calculate the temperature, estimate the temperature and composition of the eutectic point in the ternary system, MgCl2, MgF2, LaCl3. He gives you the phase diagrams of the 3 systems, the 3 binary head systems. They're all simple eutectic systems with no solubility in the solid phases. Okay, so you have here a you'll see things defined this way, of course, in the literature. This is a ternary system. Ternary system is defined as, I'm I'm going to draw it this way. So you'll see Y, MgCl2, MgF2, LaCl3. So there's your ternary system, and he gives you the phase diagrams for the 3 binary subsystems. Okay, so this is just a simple Kohler tube thing, all right? No, it's not, because you have 2 sublattices. Okay, this is not a system A, B, C, where these molecules are mixing on one sublattice, like 3 metals. These are molten, these are salts, and you have a cation sublattice and an anion sublattice. You can't get around the fact this is not a ternary system. You've got to add on the rest of it here, and here you've got to put on lanthanum fluoride. Okay, and what you're having is you've got the model, the Gibbs energy is X magnesium, X lanthanum, sorry, X magnesium, well, Y magnesium, Y chlorine, G naught magnesium chloride, plus you use the Sub Lattice model. You have and then you have 4 N members, so you've got the Y magnesium, Y chlorine, G naught magnesium chloride, plus Y lanthanum, Y chlorine times G naught LaCl3, plus you have the RT, and then you have the X lanthanum, LNX, you have the mixing of the magnesium and lanthanum on their sublattices, plus the next term for the mixing of the fluorine and chlorine on their sublattices, the whole shit. Okay. And you're using the sublattice model. You cannot possibly treat this ternary system like an A, B, C alloy system, because it's not at all the same model. And this is not a ternary system. You can have tie lines that cross the boundary quite easily. This could even be your stable pair over here, for that matter. Okay. Now, if this is a very stable pair, then most of the tie lines will lie over here. This will be a quasi-ternary system, but you still need this model. And you certainly, I know the most important, remember the most important thing in any reciprocal system like this are these G naughts. The delta G exchange is the most important term. The binary systems, all these binary systems here can be simple eutectic systems, but if your G naughts are, if your delta G exchange is very positive or negative, you're going to get all sorts of deviations in the ternary. So you need the delta G of exchange for all the phases, you need the Gibbs energies of all 4 corners, and you need the phase diagrams of all 4 binary systems, not just this and this, but this and this as well. And the data along here is really ternary. What she said is available is really ternary data, which will help you put in some ternary terms if necessary. But you must use the quasi-chemical, you must use the sub-lattice model. Okay, and you need not just data on these, data for these 3 binary systems, which it gives you. What would be enough if this were a system ABC of 3 metals? Data on those 3 binary systems is all you need. But since it's a reciprocal system, that's not enough. You need the Gibbs energies of the 4 N members, so you can get the delta G of exchange, and you also need these binary systems over here as well, because they tell you the other interactions. Okay, 2005-24 should be here somewhere. This one. All right, this is the one that's more complicated. Liquid salt solutions are usually modeled with a 2 sub-lattice model. Like sodium chloride, as we've done here. Strictly speaking, now you can do this in a solid, but strictly speaking, this is an approximation, because a liquid which lacks long-range order cannot be said to consist of more than 1 sub-lattice. You know, no matter how ordered it is, if you go far enough away, it all becomes there's no long-range order. Okay, now write an equation for the extensive Gibbs energy of a molten salt solution of sodium chloride and KCl, just the 2 salts, NaCl, KCl, in the Bragg-Williams approximation, using a 2 sub-lattice model as a function of the number of moles and mole fractions of sodium chloride and KCl. So these are the number of moles of NaCl and KCl and the mole fractions X, and of the molar Gibbs energies of the pure salts. Okay, and ignore the excess Gibbs energy terms. Okay, so that's assuming that you have 2 sublattices, as you do, the simple way that we normally do it. Now let's use a 1 sublattice model. as you're supposed to do it. If you have a one sublattice model, then you must permit the sodium, potassium, and chlorine to go on the same sublattice. So you're using the one sublattice quasi-chemical model with a great amount of short-range ordering, meaning the sodium and potassium. So you have three atoms, sodium, potassium, and chlorine. You can even forget the charges now. You have three atoms, sodium, potassium, and chlorine, all in the same sublattice. But sodium-sodium bonds plus chlorine-chlorine bonds form two sodium-chlorine bonds. The delta G for this is extremely negative, so this is pushed almost entirely over to the right. And the same thing for the KCl. In that case, this is sort of the correct model that you should use. But you're going to see that in the limit, as this becomes infinitely negative, it reduces to this model, which is mathematically much simpler. But there are also certain limitations too. So in the second equation, then write an equation using the one sublattice quasi-chemical model. I should write in here, one sublattice quasi-chemical model. In terms of the number of nearest neighbor pairs, the number of mole fraction of nearest neighbor pairs, and so on. And in terms of the Gibbs energy changes of these pair exchange reactions. For the pair exchange reactions, let's assume that delta G sodium potassium is 0. There's no ordering between sodium and potassium in this sublattice. In the limit where delta G, NaCl, and KCl are extremely negative, and along the stoichiometric join between NaCl and KCl, show by making approximate substitutions that the quasi-chemical model reduces to this model. Okay. So we will go to the equations here. And this was a Xerox of a Xerox, but I hope you could read it. And the first part one then was using the sublattice model. So the sublattice model, you're just mixing sodium and potassium ions on their sublattice. So it's the number of moles of sodium chloride, which is the number of moles of sodium times G naught sodium chloride, plus number of moles calcium, plus RT times the x1 log x1 plus x2 log x2, that's it. Okay, that's the sublattice model. Because you forget the chlorines, you're just mixing sodium and potassium on their sublattice. I'm just putting the entropy terms in, don't forget it. Okay. Now, how would we do it if we use the one sublattice model? So you'd have to have sodium, potassium, and chlorine are A, B, and C. They're mixing on their sublattice. They're mixing on one sublattice. So you've got N sodium, G naught sodium, plus N potassium. This is just like an alloy model, A, B, C, a one sublattice alloy quasi-chemical model, plus the Gibbs energy of this pair reaction over 2 times the number of moles of sodium-chlorine pairs. This is just the quasi-chemical equations for a ternary one sublattice system, plus delta G of forming the KCl pairs, plus the delta G of forming the sodium-potassium pairs, multiplied by the number of pairs. That's your simple sublattice model. Quasi-chemical model, one sublattice. Plus your mixing terms then. So this is your configurational entropy in the quasi-chemical model. So it's the ideal term RT, you mix Na sodium, potassium, and chlorine, and then you've got this other thing, RT over 2, number of sodium-sodium bonds, log x sodium-sodium over x squared sodium, x potassium-potassium over x squared potassium, sodium-chlorine over x chlorine squared, and then you have the sodium-chlorine over 2. This is just your standard quasi-chemical configurational entropy equation for mixing sodium, potassium, and chlorine, or A, B, and C. Just look in the notes. And this is the number of moles of A, G naught A, plus number of moles of B, G naught B, plus delta G of the AB quasi-chemical thing over 2 times the number of moles of AB bonds, plus you write out the entropy term. I'll forget the higher order or the second order terms. Now, then we're going to take this equation along this join, so I'm going to apply it just along the sodium chloride, potassium chloride join. And I'm going to make these delta G's of forming these bonds here, NaCl and KCl bonds, very, very negative. Okay, so I'm going to make the substitution in here that these reactions, this reaction to form the sodium chlorine bonds and the equivalent one to form the KCl bonds are extremely negative. And I'm going to apply it just along that line. Okay, so along the sodium chloride, potassium chlorine join, when you make this thing, the number of sodium-potassium bonds, the sodium-sodium bond, remember this is completely shifted to the right. So all the bonds are either sodium-chlorine or potassium-chlorine bonds. There's no sodiums, there's no cation, no potassium is next to a sodium. So the number of sodium, potassium, and potassium bonds, and the number of chlorine bonds is 0, if these delta G's are negative enough. Or the number of sodium, so the numbers are also equal to 0. The mole fraction of sodium chloride along that line is the mole fraction of sodium chlorine bonds. Along that line you have only sodium chlorine and potassium chlorine bonds, so the mole fraction, the overall mole fraction of sodium chloride is the mole fraction of sodium chlorine bonds. The mole fraction of KCl is the mole fraction of KCl bonds. The number of moles of sodium is the number of moles of sodium chloride. Number of moles of sodium plus potassium is equal to the number of moles of chlorine, because you're along that line. And the mole fraction of chlorine is 1/2 in this system. Sodium, chlorine, potassium, the mole fraction of chlorine is 1/2 along that line. The delta G of sodium chloride, this is the delta G of this reaction. This is delta G NaCl. This is your quasi-chemical parameter. Delta G NaCl is a parameter of the quasi-chemical equation, is equal to the Gibbs energy of sodium chlorine bonds minus the Gibbs energy of sodium minus the Gibbs energy of chlorine over 2. Delta G of KCl is equal to that. The number of sodium chlorine bonds is Z times the number of moles of sodium. Okay, because every sodium is surrounded by Z chlorine, so the number of sodium chlorine bonds is Z times the number of moles of sodium, which is Z times the number of moles of sodium chloride. Number of KCl bonds is Z times, etc., etc. X chlorine is 1/2. The mole fraction of sodium is the number of moles of sodium over sodium plus chlorine, which is the mole fraction of sodium chloride over 2. And the mole fraction of potassium is the mole fraction of KCl over 2. The mole fraction of KCl is defined along that line. You make all these substitutions back into that equation, simplify your terms, and you end up with, if you could do that, make all those substitutions back into the quasi-chemical equation, simplifying it along that NaCl-KCl joint, assuming that these reactions are displaced all the way to the right. Just take the limiting case, and you end up with this equation. So these first two terms here, then, you'll come out are exactly the same as this equation up here. And you have a final equation, which has a minus 2 log 2 plus Z log 2. And so for the two equations to be equivalent, this term has to be 0, and this is the same as equation 1, only when Z equals 2. Which, remember, as I said, the quasi-chemical equation is only exact. The entropy equation in the quasi-chemical is only exact when Z equals 2. So when Z equals 2, this is an exact entropy expression, and everything's coming out right. If Z does not equal 2, it's not an exact entropy expression, and this is your mathematical error in the thing. So that's one more reason, but you certainly don't want to do it this way. I mean, it's just so complicated. But you see that it does work out to the same. The quasi-chemical model does, if you have the right entropy expression, does reduce back to the Sub Lattice model. I'll let you play with things a bit. (2006) 2.5, where are we? On here. Okay, the molten salt. Here you have a molten salt solution: lithium, rubidium, fluorine, chlorine. And this is the simple Sub Lattice model where we have your G naught terms. The Y's are the site fractions, of course. Then you have your ideal mixing term, and we're just putting in the approximate Blander correction for the non-random mixing. Okay, and I'm forgetting the second nearest neighbor terms. The alpha terms, we'll assume they're small. Where the yi's are the site fractions. That is, the second nearest neighbor binary terms are assumed to be negligible, and short-range ordering is approximated by this final term. The phase diagram along the lithium fluoride, rubidium fluoride stable diagonal. So along the stable diagonal of lithium fluoride, rubidium fluoride is sketched in the accompanying figure, which has got to be down here somewhere. Okay, there you go, between lithium fluoride and rubidium chloride. So your diagram is here, lithium fluoride, rubidium chloride, that's the stable pair. And along that stable pair, you can see that you have a liquid miscibility gap. Here you have rubidium fluoride and lithium chloride are the unstable pair. Okay, so you have positive deviations along the stable diagonal for the reasons that we talked about. Okay. So, derive an equation giving the critical temperature as a function of the exchange Gibbs energy Z and the mole fraction along that line. I define the mole fraction of rubidium chloride simply along this line going from 1 to 0 along that line. Okay, so in that quasi-binary system, this is pretty close to being a quasi-binary system, meaning that all the tie lines are more or less lie in the plane, so that the diagram along this line looks like a binary phase diagram. You want the critical temperature of the miscibility gap along that line as a function of the mole fraction. Firstly, derive the equation ignoring the short-range order term, and then derive it including the final term. Show that the final term always lowers T critical and explain why this is so. So that's your T critical you're trying to calculate as a function of mole fraction along this line with and without the final term. Okay, so along the diagonal, I'm going to make, along the diagonal then, the site fraction of rubidium and the site fraction of chlorine are equal, because you're going just along the line here. So the rubidium is always equal, the number of rubidium is always equal to the number of chlorine along that line. And that's equal to the mole fraction of rubidium chloride along that line. And Y lithium equals Y fluorine is 1 minus X. So along that line, the rubidium and chlorine are in the same amounts, the lithium and fluorine are in the same amounts, so this is the mole fraction. So making these substitutions into here, then X is this X here. So I go back to the, so along that line, this should be the site fraction of lithium times the site fraction of fluorine. The site fraction of lithium is 1 minus X, the site fraction of fluorine is 1 minus X. This is the site fraction of lithium times the site fraction of chlorine, which is 1 minus X times X, and so on for the other terms. Plus 2 RT, because you're mixing here, I'm mixing the, this is your mixing term, this is just, I put a 2, you have RT X log X plus 1 minus X log 1 minus X in the cation lattice and in the anion lattice. They're the same. So this is first term for mixing the cations, the second term for mixing the anions. Minus, and then this is the short range order term, which was the product of Y lithium, Y rubidium, Y chlorine, Y fluorine, which then turns out to be, using this substitution, X squared 1 minus X squared del G exchange squared over Z RT. So that's your substitution, where X now is this X here is this X of rubidium chloride. Okay, so we're trying to calculate the critical point of the miscibility gap, and okay, as you know, that's the critical point of the miscibility gap. Miscibility gap now, since we have no mixing, no regular terms or anything here, the mixing term is going to be at in the middle, right? It's going to be at 50% because the thing is perfectly symmetrical. In other words, T critical is going to be at 50% along this line. This is a perfectly symmetrical equation, right? Okay, so I take the second derivative then. We've done this before. Along the line you have the going along the line from lithium fluoride to rubidium chloride. If you plot the Gibbs energy of mixing along that line, if you're above the critical point, it's going to look like that. If you're below the critical point, it's going to look like that. So you're taking the point here, the second derivative at this point is positive, here the second derivative is negative, the critical temperature is the temperature where the second derivative is 0 here. So this is T is less than T critical, this is T, we've done this before, T is greater than T critical. We're going to find the T. This is the T equals T critical at the point where the second derivative equals 0 at the maximum point, which is, of course, 50% in this. So I take the first derivative. I take the first derivative of this thing, and I get this. I take the second derivative of that, and I end up with all this. And that has to be equal to 0. By symmetry, as I said, T critical has to be at x is 0.5. This equation is perfectly symmetrical with respect to x, and 1 minus x is no different. So it has to be 0, T critical at x is 0.5. So ignoring the final term, if I ignore the final term, okay, T critical is 0.5. So I take this equation here for the second derivative. I substitute x is 0.5 into that equation, and I end up with this, and I set it to be 0. So the second derivative has to be 0 at x equals 0.5. So substitute x is 0.5 into that equation, and you end up with this expression here. And that must be equal to 0. So if I ignore the final term, which comes from the short-range order, then these first two terms equal to 0. So the critical temperature is minus delta G exchange over 2R. The delta G exchange, as I wrote the delta G exchange here, I wrote it as negative. So the delta G exchange is negative going along that line. This is the stable pair. So this delta G exchange is negative. So the T critical is, of course, positive. And it varies as delta G exchange. As delta G exchange is twice the delta G exchange, gets you twice the T critical Kelvin. If you include the final term, then you get T critical is equal to this. Hence T critical is lowered by adding this final term. The final term being always negative, you'll see. Think about it, you'll see that by putting in this final term, you always lower the critical. The solution to this equation is always at a lower temperature. Okay, and the reason is then that the critical temperature is because the rubidium fluoride and the lithium fluoride don't want to mix. The rubidium likes to stay next to the fluorine, the lithium likes to stay next to the chlorine. If you make a mixture, you're forcing them to be next to the neighbors they don't want to be next to, so they make a miscibility gap. But if you permit some non-randomness, then within the actual single-phase region, the rubidium and fluorine can cluster, the lithium and chlorine can cluster, they can stay next to each other without having to separate into two phases so much. So it stabilizes the liquid and they lower it. Or the other way of looking at it is anytime you remove a constraint on your model, the constraint was at first, without that final term, the constraint is that it's a random mixture. Now you're saying it doesn't have to be a random mixture. So you remove a constraint, the liquid will always then, using the constraint, will lower its free energy. Free energy with the removing constraint will always be lower than the free energy with the constraint, because the system always tries to lower its Gibbs energy. Give it another chance to do so, it does so. So removing the constraint, you lower the Gibbs energy of the system, so it'll surely make it more stable and lower the miscibility gap. Questions about these? Trying to show you, the mathematics, but apart from the mathematics, it's like physically why, what's going on, and what are the important terms and what aren't the important terms, and so on. Clearly, again, the important term in determining the miscibility gap is this exchange Gibbs energy. All these other terms which we've ignored, the alpha terms, but if you put them in, it would make it much more complicated mathematically, but it doesn't get around the fact that this is the major thing that's causing your miscibility gap. Short range order always is going to stabilize the phase. Some 2008 2. Okay, so you have a very dilute solution of calcium fluoride, N calcium fluoride moles of calcium fluoride, and N sodium chloride moles of sodium chloride. So the number of moles of calcium fluoride is much less the number of moles of sodium chloride. where you define the overall mole fraction is simply defined this way. Write an expression for the activity of sodium chloride, which is a solvent, as a function of x, and the limit as x calcium fluoride approaches 0 for a liquid solution and a solid solution. Oh, sorry. There. Maybe I should leave this. Did this all make sense to you, or have you had some problems with this? Because I was going to get on to molten salts. Well, okay, let me. I have the impression this entire problem set here has given you problems, or no problem at all? Does this all make sense to you, or you're starting to find it sort of... No?
Maybe we need more problems to solve more time.
Okay. Did you succeeded in solving some of these problems, or...?
No, it's not completely.
Not completely. But the general concept? Let's, these last, what was the last one? I'm going to leave that one. I'm going to 2009 to first. Okay, this one, 2009 too, is the last one. A liquid solution, sodium calcium chlorine, is prepared by mixing 1 mole of sodium chloride, 2 moles of KCl, and 1 mole of KF. Calculate the site fractions for the 4 ions. The Gibbs energies of the pure salts, absolute Gibbs energies of the pure salts at 1000 Celsius are. The 4 binary common ion systems are approximately regular, so you've got your excess Gibbs energies for your 4 binary edge systems. Calculate the Gibbs energy of the solution at 1000 Kelvin using the compound energy formalism with the first order Taylor expansion approximation for short range ordering, which is the same expression we just did. So this is, I think, pretty straightforward. You're just plugging numbers into an equation here. Okay, so you have your 4 sodium, potassium, chlorine, fluorine system. You're given the number of moles of sodium chloride. This is what you actually put in out of your bottles in the laboratory. 1 mole of sodium chloride, 2 moles of potassium chloride, 1 mole of potassium fluoride. So the number of moles of sodium ions is 1. Number of moles of chlorine ions is 1 plus 2. Number of moles of potassium ions is 1, and the number of moles of fluorine ions is 1. So the site fraction of sodium is sodium over sodium plus potassium is 1/4, which is 1 minus Y potassium. The site fraction of potassium is 3/4. The site fraction of chlorine is chlorine over chlorine plus fluorine, which is 3/4, and Y fluorine is 1/4. Total number of moles is sodium plus potassium, which must be equal to fluorine plus chlorine, which is 4. Alright. So the the 2 sub lattice compound energy formalism with the simple approximation for random mixing is given by this. That's your simple equation with your site fractions times your G naught, your mixing terms. And then you have your alpha terms. So Y sodium, Y potassium, Y chlorine times the excess Gibbs energy term for the sodium chloride potassium chloride system. Sodium potassium fluorine times the Gibbs energy, excess Gibbs energy term for the sodium fluoride potassium fluoride system, similarly for the other two, minus y del G exchange squared over ZRT, where the del G exchange is the Gibbs energies of sodium chloride plus Kf minus the Gibbs energies of sodium fluoride and KCl, which is given by this. So putting these site fractions for the actual solution into the equation and solving the whole thing out, you end up with the molar Gibbs energy for the solution just by making all the substitutions. So the total Gibbs energy is the total number of moles times G, which is 4, which is 2.505.52 megajoule. It's making the substitution. Okay. The point here is mainly, I suppose, making the substitutions. These terms, maybe be sure that you understand where these terms come from. This is Y sodium. In the sodium chloride KCl system, Y chlorine will be 1, and this is the excess Gibbs energy of mixing in the sodium chloride potassium chloride system, multiplied by Y chlorine, which is less than 1 as you get off into the ternary system. Okay, maybe it was a little premature in putting that 2008 2 in. So let's, okay, I'm going to give you a little lecture now, and then we can go back and take a look at that one. This, so I'm going to talk a little bit now about molten salt. So we're going to number 21 here. So remember number 21, if you go way back, this was dealing with the simple quasi-chemical, sorry, the Sub Lattice Model for the salt, sodium chloride, KFF. This is just the equation we've been dealing with again. You have the Gibbs energies of the end members, then you have the mixing term on each sublattice, and the GXS term here I'm forgetting about now, the second order terms and so on. I'm just dealing with the G naughts and the ideal mixing term, the two most important terms. And I remember I said from this I wanted to get an expression for the Gibbs energy of sodium chloride, for the activity of sodium chloride in this mixture. So this goes back. So here we have sodium fluoride, potassium fluoride, and I'm trying in that system to get an expression for the activity of sodium chloride. And the main terms are the end member terms, the product of the site fractions times G naught, the 4 terms, plus the ideal mixing term on each sublattice. GXS terms are your alpha terms, plus your short range order correction, which we'll ignore for the moment because these are the most important terms, especially in dilute solutions. And going through this again, the total number of moles is the total number of cations, which is equal to the total number of anions in this monovalent solution, the mole fractions of sodium and the site fractions of sodium, the site fractions of fluorine, and so on. And remember I said the Gibbs energy, the chemical potential of sodium chloride by definition is dG, dN, and sodium chloride. So the chemical potential of sodium chloride is, you take a a solution with the Gibbs energy G, you add N NaCl moles of sodium chloride to it, you take your solution, you throw in a little bit of sodium chloride, keeping the number of moles of potassium and fluorine constant, and that is your definition of the chemical potential of sodium chloride, where big G is little g times N total. And the thing is, you're adding sodium chloride. You're taking your solution, you're putting in salt, sodium chloride, so you're adding the DN sodium chloride, is you're adding sodium and chlorine in equal amounts. So DN sodium chloride is DN sodium, which is DN chlorine. That's the clue here as to what you're dealing with. So we did the mathematics. Gives energy of sodium chloride. If you take this equation up here and differentiate it with respect to N sodium chloride, taking account of this whole thing, and I'm sure you check this out at home, you end up with, after you collect all your terms, that the chemical potential of sodium chloride is equal to the chemical potential of pure sodium chloride, which came from this term after you collected everything, plus these terms here. RT log activity of sodium chloride then is, by definition, G minus G standard. So RT log activity of sodium chloride is G minus G naught, and you end up with a nice simple expression that RT log activity of sodium chloride is RT log product of the site fractions. And then you have this term here, which is the product of the site fractions of the other two components, not sodium and chlorine, but Kf times delta G exchange, plus your excess terms which come from those other terms that we've ignored. They're secondary, so we forget all about this. Okay? Okay, so if your exchange Gibbs energy is 0, then the activity of sodium chloride is just X sodium times X chlorine, the product of the site fractions. If your delta G exchange, well, we went through this before, if it's negative, then you have a positive term along here, which brings up the liquidness and so on. But let's suppose now that X sodium chloride, the mole fraction of sodium chloride is approaching 1, so you're in this region up here. You're around sodium chloride. In that case, this term here goes to 0 simply because X potassium and X fluorine go to 0. Okay, so as X sodium chloride approaches 1, the activity of sodium chloride approaches the product of the site fractions. X sodium times X chlorine. This is the solvent. Okay, so if you're in a concentrated solution, the activity of the solvent approaches simply the product of the site fractions. Because this term, no matter how big delta G exchange is, this term, this XKXF in front of it's going to make it small. And these terms here too, you can show also go to 0 in that. The GXS terms are also going to go to, by second order nearest neighbor terms are going to go to 0 by Henry's law. So for the solvent, if you're in a corner, the activity of the solvent is just the product of the site fractions. Which I should be writing as small y, but I'm not. I'll get product of the site fractions. Okay, let us suppose then that we're dealing with a mixture of, that's for a monovalent salt, suppose we're dealing with a mixture of divalent salts, let's say I'm taking calcium chloride instead of sodium and calcium fluoride. So I've got calcium chloride, calcium, so this is going to be a Kempken. Well, not necessarily. Yeah. So the calcium and potassiums are mixing and the fluorine and chlorine are mixing. And I'm going to calculate the activity of calcium fluoride using the same thing. Okay, so I'm going to write out the okay, first of all, just notice, by the way, that this term here, the term we're dealing with is that Y sodium, I said in the very dilute solution, these terms, this exchange term goes to 0, this goes to 0. This is the only term we're interested in, RT log activity of solvent equals RT log product of the site fractions. This is the most important term when sodium chloride is rich. And this term here came from the ideal entropy term, from the entropy mixing term. Okay. This is the only term that really matters when you're in a concentrated. This is the only term that matters here for the activity of the solvent when you're in a really concentrated solution. We did this before with a single sublattice. When you're going up to this is Rayleigh's law for a sublattice model, is what it is. When you're going in for Rayleigh's law for a single lattice system, XA, XB, as the mole fraction of A approaches 1, the activity of A approaches the mole fraction of A. That's for a single sublattice. If you have a two sublattice model, then as the activity of sodium chloride approaches 1, the activity of sodium chloride approaches not the mole fraction of sodium chloride, but the product of the site fraction. So this is Rayleigh's law when you have two, or it's Rayleigh's law on one lattice times Rayleigh's law on the other lattice, if you like. Okay, you sometimes will see this written that RT log activity of sodium chloride equals RT log activity of sodium plus RT log activity of chlorine, which is RT log X plus RT log X. This isn't quite right because you really can't talk about the activity of a single ion. But okay, so this is simply Rayleigh's law for a sublattice model. And Rayleigh's law, as you know, simply says that as you approach the pure component, the only term that counts anymore is the ideal mixing term, because the ideal mixing overshadows any second order effects you might have. All right, so let's suppose now we have a charge asymmetric system where we have calcium chloride and potassium fluoride and calcium. So we have two different systems here then. So we would have an entropy term. In this case, we would have an entropy term. No, it's not on there. The chemical potential of calcium chloride is going to be dG dN CaCl2. Okay, so write out the entropy expression for your system. Say you have your system calcium, potassium, fluorine, chlorine. Write out your Gibbs energy expression for that system. It's going to be the product of the site fractions, etc., etc. This doesn't really matter. All that really matters is this term here. Okay, so your entropy expression is going to be RT X calcium log X calcium plus X sodium log X sodium for mixing the calcium and sodium on its sites, and you're going to have the RT X fluorine log X fluorine plus X chlorine log X chlorine on its sites. Okay. You're going to have the same sort of term. You're mixing calcium and sodium on their sites, you're mixing fluorine and chlorine on their sites. Okay, so it's going to be the same entropy expression, but now you're going to have Gibbs energy chemical potential is dG dN calcium chloride. We're doing the same thing here. The G of sodium chloride was G dN sodium chloride. dN sodium chloride is equal to sodium plus chlorine, because you're adding sodium chloride, you're adding the sodium and chlorine in equal amounts. Now what you have to notice is that the only difference really when you apply this equation, when you do what you're doing here, you're trying to get the chemical potential of calcium chloride, is you've got to realize that as you're adding calcium chloride, the number of moles of calcium chloride which you add is equal to the number of moles of sodium, but that's equal to 1/2 the number of chlorine. Okay, so the number of moles of sodium, you're adding every time you add a calcium chloride, you're adding 1 mole of calcium, number of moles of sodium calcium, dN calcium. So the number of moles of calcium chloride which you're adding is equal to the number of moles of calcium and 1/2 the number of moles of chlorine that you're adding. So when you do the substitution, there's going to be a 1/2 here. And when the whole thing comes out, comes out really. So in the limit, as X calcium chloride approaches 1, what you're going to get is you're going to get RT log activity of calcium chloride equals the site fraction of calcium times the site fraction of chlorine squared, because we have 2 chlorines here. So this is your ideal activity of calcium chloride in the solution as the mole fraction. As you get a this is Rayold's law for a sublattice model with calcium chloride, where the calcium and the two chlorines are independent ions. Or, and to be completely general then, doing the same thing, you would say if you have a system, say you have A2X3, this is your salt, A2X3, and you have the mole fraction of A2X3 approaches 1, so you're talking about the ideal limit for the solvent A2X3 in a sublattice model. The activity of A2X3 then in Rayold's law approaches the site fraction of A squared times the site fraction of X cubed, and so on. Just your limiting ideal equation. Not in the, no, because the entropy term, remember, is always in terms of the mole fractions.
Yeah, but we usually multiply by the equivalent fraction.
That's if this is the Gibbs energy per equivalent. If it's the Gibbs energy per mole, you would just have to put, say, a 2 in here or something. Yeah, you got to be careful that you got the right number of, that you defined number of. I want you to try this out yourself and prove it to yourself that you can.
Okay.
Okay, but it works out.
Okay.
Now, if you don't like the squares, well, okay, the other way, looking at the square term, let's say we just had a single sublattice system. I have a system AB, which is an ideal solution of A and B. Ideal solution of A's mixing with B's. Okay, if the activity of A, the mole fraction of A, what is the activity of A2? It's the mole fraction of A squared. No. Even if it isn't an ideal solution, the activity of A2 is the mole fraction. If the activity of A2 is the activity of A squared. Okay. Chemical potential of A is equal to G dNA. Chemical potential of A2 is equal to dG dNA2 by definition. A2 doesn't mean I have an A2 molecule, it's just I define a component as A2. Okay. dNA2 equals 1/2 dNA. So I take my big solution here, which has a Gibbs energy of my liquid, which has a Gibbs energy of G. I add DNA moles of A, and the change in G with DNA moles of A gives me the chemical potential of A. If I add DNA 2 moles, which is 1/2 DNA, that gives me the chemical potential of A2, which is going to be twice then the chemical potential of A. Okay, so the chemical potential of A2 is going to be twice the chemical potential of A just because of the... Okay, so if the ideal activity is the mole fraction, the ideal activity of A2 is the mole fraction of A squared. So the ideal activity of calcium chloride is the site fraction of calcium times the site fraction of chlorine squared. You're adding 2. You're adding 1 calcium and you're adding 2 chlorine, so it gives you twice the entropy, it gives you twice the... Okay, so now let's go back to 2008, number 2. Alright, so now we have a very dilute solution of calcium fluoride and sodium chloride. Okay, write an expression for the activity of sodium chloride as a function of calcium fluoride in the limit as the mole fraction of calcium fluoride goes to 0 for a liquid and for a solid. So sodium chloride, NaCl as a solvent, you're adding a small amount of calcium fluoride. Do I have that answer on here? I probably don't. Okay, so for a liquid solution, this is the point here, is that you have a so we're going to deal with the liquid first of all. So now in the liquid you have sodium chloride, you have calcium fluoride, but there's no vacancies are formed. The sodium and calcium mix on their sublattice, and the fluorine and chlorine mix on their sublattice. Okay, and the number of sublattice sites is simply given by the number of ions on the lattice. Temkin model for a liquid. Okay, the liquid conforms. In that case, the activity of sodium chloride then is the site fraction of sodium times the site fraction of chlorine, as we just said. In the limit, you're talking about the limit as active mole fraction of sodium chloride goes to 1. This is Reynolds law. The activity of the solvent is simply the site product of the site fractions. Reynolds law for a sublattice model. Okay, so it's the site fraction of sodium times the site fraction of chlorine. The site fraction of sodium in this case, the site fraction of sodium is simply the number of moles of sodium over the number of moles of sodium plus the number of moles of calcium in the Temkin model, and that's the overall mole fraction of sodium chloride. Okay. You're going along the join. We're mixing sodium chloride with calcium fluoride. I'm going along this join here. I'm going along. I'm taking sodium chloride and I'm adding calcium fluoride to it. Okay, so the site fraction of sodium is sodium over sodium plus calcium. Sodium over sodium plus calcium is simply the mole fraction of sodium chloride as you're going along that line. The site fraction of chlorine is chlorine over chlorine plus fluorine, which is the number of moles of sodium chloride. I'll write the whole thing out. The number of moles of sodium chloride equals the number of moles of sodium equals the number of moles of chlorine. The number of moles of calcium fluoride, which you're adding, is equal to the number of moles of calcium equals 1/2 the number of moles of fluorine. The mole fraction, overall mole fraction of sodium chloride is just the overall mole fraction of sodium chloride is simply the number of moles of sodium chloride, which you're adding, divided by the number of moles of sodium chloride, plus the number of moles of calcium fluoride. And so on, and that's equal to then. So the number of moles. So the site fraction of sodium is equal to that, which is the mole fraction of sodium chloride. The site fraction of chlorine is the number of moles of chlorine over chlorine plus fluorine, which is the number of moles of sodium chloride, over the number of moles of sodium chloride plus twice the number of moles of calcium fluoride. The number of moles of fluorine is twice the number of moles of calcium fluoride. Every calcium fluoride gives you 2 moles of fluorine. So this is the mole fraction of sodium chloride over the mole fraction of sodium chloride plus twice the mole fraction of calcium fluoride, which comes out to x sodium chloride over 1 plus x calcium fluoride. Then, going back to this formula, the activity of sodium chloride then is the site fraction of sodium, which is the mole fraction of sodium chloride, times the site fraction of chlorine, which is equal to that. So that would be your activity of sodium chloride along that joint in the Temkin model. Everybody happy with that one? Mr. Kim, you look unhappy. That's okay? That's okay? Okay. Now for a solid, however, things are different. In a solid, each calcium ion produces 1 cation vacancy. So if you have the solid, you cannot just mix the calcium and sodiums because you have a rigid lattice. So you will have your sodium chloride lattice, sodium chloride in the 2 sublattice model. See that wrong? Minus. And so So then we're going to put a calcium is going to go in here, so this will be your calcium will go here. The chlorines stay the same, but we end up with a vacancy. Okay, and the calcium and the vacancy form two independent particles. All right, so now each calcium ion produces one cation vacancy. Okay, so now the number of sodiums equals the number of sodium chloride. The number of moles of chlorine equals the number of moles of sodium chloride. The number of moles of fluorine equals twice the number of moles of calcium fluoride. The number of moles of calcium equals the number of moles of calcium chloride, and that's equal to the number of moles of vacancies. So every calcium chloride produces the calcium and the vacancy. So the site fraction, so you're still going to use the same equation. The activity, it's still a solution that's very rich in sodium chloride, so Raoult's law still applies. So the activity of sodium chloride in the ideal Raoult's law limit is still simply the site fraction of sodium times the site fraction of chlorine. That doesn't change. That's just the thermodynamic equation. The activity of the solvent is the product of the site fractions. Okay, but now the site fractions are going to be different because you've got vacancies in there. The site fraction of sodium before, in the liquid, the site fraction of sodium was sodium over sodium plus calcium. Now it's sodium over sodium plus calcium plus vacancies. You have three species occupying the cation sites. You have sodiums, calciums, and vacancies. So this is the site fraction of sodium, which is the number of moles of sodium over the total number of sites. Total number of sites is sodium plus calcium plus the number of vacancies. Because the calcium and vacancies are independent particles which are mixing random. Number of moles of sodium is the number of moles of sodium chloride, the number of moles of calcium is the number of moles of calcium, and the number of moles of vacancies is also the number of moles of calcium. So now you've got N calcium plus N calcium. So this is the mole fraction of sodium chloride over the mole fraction of sodium chloride plus twice the number of moles of calcium fluoride for the cation sites. Okay? Site fraction has changed because you got total number of sites is different now than it was before. In the liquid, the total number of sites was simply the number of moles of sodium plus the number of moles of calcium. Now the total number of sites is sodium plus calcium plus vacancy. Okay, so this term. The second term is the same as it was before because the chlorines and fluorines have the same charge. And so now the activity is the same thing. It's the site fraction of sodium, which is this term, times the site fraction of chlorine, which is this term. So you get this, but you see that's different from, it's bigger. Smaller. The activity of sodium chloride has been decreased. The second term here is the same as the second term here, but the first term here was X sodium chloride. Now it's X sodium chloride over X sodium plus 2X calcium, which is 1 plus X calcium. 1 plus X calcium. This is X sodium plus 1 plus X calcium. This is the same as this. Okay, so you have a denominator in here, so that lowers the activity of sodium chloride. So this activity of sodium chloride is smaller than this activity of sodium chloride, so this solution is more stable. You decrease the activity. How does that relate back to the entropy? Well, you have more particles mixing, you have a larger entropy. In the Kempkin model for the liquid, you have only calcium and sodium. Now you have calcium vacancies in sodium. You have twice as, every calcium is basically introducing two particles on the cation site, so you've got twice the entropy. So the solution has a higher entropy, so it's more stable. Okay, so you lower the activity. But the point is here that the activity, the ideal limiting, this is Raoult's law for a sub-lattice model. In the limit, the activity of the solvent is simply the product of the site fractions. But when you calculate the site fractions, you have to take into account everything that's on the lattice, not just the overall sodium and calcium. It's if something else is on the lattice, like the vacancies, you've got to take that into account. And of course, if you had calcium chloride, then you would do it the same way. I can give you have to do a couple of other examples. what's this going to do to the, okay, so you see that this, if you compare these two equations, the difference between the two is that this equation here has one more denominator, 1 plus X calcium fluoride in the denominator. So the denominator is greater than 1. This 1 plus X calcium fluoride is always greater than 1 in the denominator, so that lowers the activity of sodium chloride. Okay, so this always means that this is total entropy. Remember, the Reynolds law says that in the limit of mole fraction of the solvent going to 1, it's only the ideal entropy. Everything becomes ideal, it's only the ideal entropy term. Everything is ideal. It's an ideal solution in the limit, is Reynolds law, as far as the solvent's concerned. But you just have to consider now, not only you have an ideal mixture on this sublattice and an ideal mixture on this sublattice. Reynolds law simply says for the solvent, as you approach the mole fraction of something equals 1, its activity is simply given by an ideal entropy expression. That's all Reynolds law is, but you have to take into account the two sublattices. And as I showed you another example then, what this would do to a phase diagram, talked about this before too. If you had here, say, sodium chloride, and you're adding something like, what's this calcium chloride? Okay, you're adding calcium chloride, you're adding a ACl2 versus temperature. This will give you a phase diagram that tends to have this is liquid and this is solid. The reason being that the solid has a higher activity than the liquid. So as you add this, you take sodium chloride and you add this asymmetric salt, which has a different charge, and by introducing the vacancies, you're stabilizing the solid more than you're stabilizing the liquid. The entropy of the solid, because of this term here, increases more quickly than the entropy of the liquid of the same composition. So the solid is entropically stabilized relative to the liquid, so it tends to push up the liquid solid curve. Now, this whole equation here assumes that the calcium ions and the vacancies are two independent particles which mix randomly on the sites. And this is always the case if you have a very dilute solution. If you have a very dilute solution, that very dilute solution so here you have your calcium ion, here you have your calcium ion, and over here you have your vacancy. And those vacancies and the calcium ions tend to go off and form their own separate because that maximizes the entropy. Now, as you get to be, however, the calcium 2+, this is a center of positive charge in the lattice. This has one charge more than the lattice normally has. This vacancy has one less positive charge. Okay, so relative to the entire lattice, this is a center of a positive charge and this is a center of negative charge. They're going to tend to attract each other. The vacancies and the calcium ions are going to try to move next to each other like this, so the vacancies and the calcium ions stay next to each other, forming pairs. That's more stable because this is a positive charge, and a net positive charge, and this is a net negative charge. So they'll tend to form associates. Calcium vacancies will tend to form an associate because of the enthalpy effect. Okay. However, if you had very, very dilute solution, everything flies apart. That's also called Ostwald's dilution law, if you like. Basically, if something's dilute enough, it'll fly apart. If you have O2 gas, oxygen likes to form O2 gas. O2 gas can be in equilibrium with two monatomic oxygens. So divalent oxygen in the gas phase is in equilibrium with two monatomic oxygens. And you'll have an equilibrium constant, which is PO2 over PO squared. But as the total pressure gets lower and lower and lower, okay, what happens is this equilibrium is shifted to the left, right? If you have extremely low pressure, then you're going to have mainly monatomic oxygen. If you have infinitely low pressure, you'll have only monatomic oxygen. This is all, okay, this equilibrium, as you lower the total pressure, will shift this way. the oxygen tends to come apart. As you increase the pressure, you force it this way. As you decrease the pressure, increase the volume, the thing's going to go this way. Decrease the volume, you force the oxygens together. Okay, the oxygens want to get together to form O2s because O2 is more stable in terms of enthalpy, H, than is oxygen, but the O monatomic oxygen forms because it's entropically more stable. You got two of them. More likely just to fly apart. That's exactly the same thing here. If you go to extremely dilute solutions, this is like a pair. This is like a molecule, calcium vacancy. This has a negative energy, just like O2 has a negative energy. So they're going to try to come together. And if you have lots of calciums and vacancies, you're going to get most of them will be forming pairs. Just like most of your oxygens will form O2s, but if you have a dilute enough solution, just like you have a dilute enough solution of oxygen, they're going to fly apart and not come back together again. Okay. So as you approach very, very dilute solutions, the calciums and vacancies come apart, but as you get more concentrated solutions, then they're going to come together. That's why this effect here is really only very small. So this type of equation really is only going to apply up to 1 or 2% depending on the system. And then as you get further on, then you're going to start to have cation vacancy associates form, and it's going to come back down again. In that case, the calcium and vacancies really now only form essentially one foreign particle. In that case, you basically forget the vacancies. The vacancies no longer are in the denominator. So if you had a solid solution that was quite rich in calcium, basically you can forget the vacancy. Why can you forget the vacancy? Because it's connected really to the calcium. The calcium vacancy is just an independent particle. The vacancy is not independent. In that case, you revert back to this equation. So this equation would hold for the solid for a very dilute solution, and then as the solid becomes more and more concentrated, it reverts, goes back to this, back to that solution. Over for the liquid, as always applies. Okay, let's take a break.